Now let's talk about implicit differentiation. So, as an example, on the surface given by 2x squared plus 7xy plus xz plus 5z squared equals 31, what is the partial derivative of z with respect to x at this given point, p equals 1, 1, 2? It would be easy if z was a function of x and y, like z equals something. Then we could just do a regular partial derivative like we've been talking about. But we don't have this written as z equals a function of x and y. So it's not explicitly written as a function. Well, if it's not explicitly a function, we can still treat it as an implicit function and use implicit differentiation. So in this given equation, we'll differentiate both sides with respect to x. For this first term, the derivative or partial derivative, we're taking the partial derivative of each side. So for the first term, the partial derivative is 4x. For the next term with 7xy, we're treating x as the variable. We're treating z as a function of x and y, and we're treating y as a constant. That's how partial derivatives work. X is the variable and the other thing, y, is a constant. So here 7y is a constant times x, and the partial derivative would be 7y. Next, for this term, x times z. So this is a non-constant function, x, and z is also a function. So we've got two functions multiplied together. That's a product of functions, and we have to use the product rule. So we'll use the product rule for this term. We would get z when we differentiate the x, and then we leave the x alone and differentiate the z. Sorry about that. X partial z partial x. For the next term, now we have a function that gets squared. So we've got a z function inside of a squaring function. That's a chain rule. A chain rule with z inside and squaring outside. So and also a constant multiple of 5. So the derivative of squaring is 2z using the power rule. The 2 comes in front, and then you'd multiply by the derivative of the inside, partial z partial x. And now we've reached the end of the first side of the equation, and we go to the other side. This is a constant, and the derivative is 0. All right, so in our implicit differentiation, we got an equation that involves x, y, z, and the derivative, partial z partial x. The derivative is what we want. So now at this point, we can just use algebra to solve for the derivative we're looking for. So let's group together all the terms that don't have that derivative, and then all the terms that do have that derivative. And that tells us that the derivative we're looking for is minus 4x plus 7y plus z over x plus 10z. So if you are comfortable with implicit differentiation in single variable calculus, this is essentially the same just with partial derivatives, so we're treating y as constant, there's just an extra variable, but then it's just a constant anyway, and it gets back to being pretty similar to the implicit differentiation in single variable calculus. In the remainder of the slides, I'm just going to talk about what is an implicit function anyway. So if you feel confident about that, then you can sort of skim through it rapidly or skip it. But when I talk to students, a lot of students have a kind of shaky grasp on what an implicit function means. So, for example, you can ask yourself, this answer that we got has x and y in it, but it also has z. Is it okay for it to have z in it? What do you think? Well, the answer is yes, it is okay. It is okay for the derivative of z to be dependent on z. Let's take a look at why that is. The answer to that question, in order to answer that question, let's step back and be clear about what is an implicit function. So here we have a pretty familiar equation, x squared plus y squared equals 1, equation of a circle. This does not give y as a function of x. This is not an equation like y equals something with x in it. And if we graphed it, or if we plotted this equation, the curve defined by this equation, we would get this circle. It's not a graph of a function. It violates the vertical line test. Maybe it doesn't violate it, maybe it just fails. Maybe that's a better word. It fails the vertical line test, right? Vertical lines cross this at 2 points. When you input an x, you're supposed to output one y, not two outputs for a function. But we can, but at almost any point on this circle, we can define a function near there. If our point was up here, then we can define a function that has this part of the graph. And maybe then in this example, we can actually solve for y. This graph would be y equals square root 1 minus x squared. If we picked a different point on the circle, maybe this point over here, then and we wanted to have a little piece of graph around it, a little graph of a function, we would have to use minus square root 1 minus x squared, right? So the idea is that for any point on the circle, somebody gives you a point and you want to find a graph that works for that point. So if the point was on the top half of the circle, you would use square root. And if the point was on the bottom half of the circle, to have a graph that works for that point, you would use the minus square root. So which one you use either square root 1 minus x squared or minus square root 1 minus x squared, isn't determined by x only. You need y also. Like if I told you that x was 0, then it could be y equals plus 1 or y equals minus 1. Which one is it? So that is the reason why in the derivative formula it's okay for the, like if I was doing the derivative of y, it's okay for y to show up because which y you pick affects what function you're drawing. Another example is this equation, x squared minus xy plus y squared equals 1, maybe a little bit less familiar. If you plot this with a program or just plot some points, it turns out to be a tilted ellipse. So this is not going to be super accurately drawn, but it's a tilted ellipse. And again, it fails the vertical line test. Any vertical line crosses this twice. So it's not an explicit function, but it could be an implicit function. So we could take sort of the top half of this graph, of this ellipse, to be one function, and take the bottom half of the graph to be another function. It kind of breaks down at the vertical points on the two sides, but we get two functions like that. I went to great lengths to figure out a couple of points on this ellipse. So let's take some example points, and this is just a semi-random choice of example points. XY could be 3/7, 8/7, or the other example point would be 3/7 minus 5/7. And I'm going to make a very rough drawing. 3/7, 8/7 is up here in this green dot, and 3/7 minus 5/7 is down here in this green dot. It has the same x coordinate, but the y coordinate is different. So okay, this drawing is not super precision drawing, but that's roughly what it looks like. And if you look at it, the tangent lines look like they're going to have pretty different slopes. We can actually figure out the slopes, and perhaps it's worth doing that just for practice with implicit differentiation. Let's find those slopes, partial of y with respect to x, or maybe it would just be dy dx. There's really only one variable here, so it's not so partial. Well, from implicit differentiation, 2x, and then we have a product rule xy, so y plus x times dy dx. And then with y squared, we have a chain rule with y is the inside function and squaring is the outside function. So 2y dy dx. And on the other side of the equation is 1. So that's a constant, so the derivative would be 0. Now we can group the terms that don't have a dy dx, and we can group the terms that do have a dy dx, and now we can solve for dy dx. So we'll get minus 2x plus y divided by minus x plus 2y. So dy dx of the upper point, 3/7, 8/7 at the upper point I'm going to a little bit skip over the fraction arithmetic. We get 2/13, and that aligns with having a slight positive slope, but very gradual. At the other point, the 3/7, negative 5/7, when you put these in to the expression we found, you get 11/13. So still a little bit less than 1, but closer to 1, so a little bit steeper than the first one we drew. So despite this drawing not being super precise, it's still in the ballpark. It shows those slopes. And that's why this derivative can have a y in it. If you only know the x, if you only said the x was a 3/7, that wouldn't be enough to tell you the derivative. You have to know the x and you have to know the y value in order to find out that slope. Well, this example and the previous page, the circle, were single variable examples that you could have seen in your previous calculus class. I hope that it has helped clarify what's going on. I hope it's been helpful, but just to finish, let's look at one example that's multiple variable. So let's look at one example here, which is x squared plus y squared plus z squared equals 1. That is an equation of a sphere, a surface, and it's not a graph of a function where z equals f of xy. It fails the vertical line test. If I had a given value of xy and we drew the vertical line through that point, then it would cross the sphere at 2 points instead of 1. So that's a given xy value in the xy plane, and there are 2 z values for the sphere that go with it, but a graph should only have 1 z value. But we can, I'll draw the sphere again. We can cover this with 2 hemispheres, a top hemisphere where we put one function, and it's not secret what it is, right? It's just z equals square root 1 minus x squared minus y squared. And we can cover the bottom hemisphere with another function, and again, it's not secret what this is. Z equals minus square root 1 minus x squared minus y squared. And things get, some things are fine and some things are a little bit complicated at the equator where they join together. You have vertical tangent lines, so infinite derivatives, that kind of thing, on the equator where those two functions join together. If we found the partial derivative of z with respect to x, I'll skip the steps, but you would end up with minus x over z. This is another example where it's not enough to know x or x and y. You also have to know the value of z in order to know that derivative, because for a given x and y value, it could be positive z or negative z. So you have to know whether this z is positive or negative in order to know which side you're on. Okay, in closing, I hope this has helped clarify what an implicit function is, and some simple examples, and the reason why these derivatives have the function itself in them. That is not a circular definition. We're not defining z in terms of itself. We're just saying that the derivative is defined in terms of z. We're not defining z in terms of itself. We're defining the derivative in terms of z. So I hope these examples have helped clarify. Of course, things could be more complicated, right? You could have, instead of just a top layer and a bottom layer, you could have a sort of S-shaped thing where then you would need to do three functions, right? You'd need to do a function on top and a function in the middle and a third function on the bottom part. So you would need three functions for this shape. If you wanted to cover this shape with graphs, you would need 1, 2, 3 graphs to cover the whole thing. And so, you can imagine it going on from there. So that's why implicit differentiation is useful, right? Because instead of solving for each of these things, we can just skip all that solving and just go straight to the implicit differentiation. It's pretty handy. Well, I hope it's been helpful. Thanks for watching. Bye.